Dr. Buckley here. Thought I'd give you a quick run. I don't know how quick it is, but I'll give you a rundown on the upcoming experiment on visible spectra, what's called Beer's Law, which I never really use that term, and nanoparticles in this particular laboratory. You'll see a little bit about the background of the experiment. You also see some of the technology things, how we're going to use some of the technology which you haven't seen before yet. It's basically two parts of the experiment. First part, we're going to look at the effects of path length and concentration on the absorbance of light that we see through different colored samples. In the first part, looking at path length, we'll take a look at some plastic strips we've got to kind of pile those up inside of a spectrometer, see what happens to my absorbance settings. In the other part, for concentration, we'll look at various food colors and food coloring types of things. In the second part, we're going to investigate the effect of silver nanoparticle size. A nanoparticle, if you remember the word nano, 10 to the minus ninth, that's like a billionth. That's a billionth of a meter. Nanoparticles on the order of 100 nanometers or less in diameter, and they have interesting color properties, even though you may have the same materials. Go back and think about your electromagnetic spectrum you were introduced to earlier in the semester. And when you do, you might remember you have short wavelength things over here, longer wavelength things on the right-hand side. In this particular image I've got here, it's extracted the visible portion out here, and it's very much not to scale. This 400 and 700, 800 nanometer range is a really, really tiny part of what you see in this particular drawing. You might remember down here, Roy G. Biv, there's Roy, red, there's orange. Over here, there's your yellow, there's your green, there's your blue, there's your indigo, and there's your violet. So he's there kind of backwards. And so he's like a VBG or something like that. But that's the colors, that's the arrangement you see these colors in based on their wavelengths. We're going to focus on the visible part. Now we can do this in different spectrometers and look at different parts. We're going to look at a visible spectrometer and see what happens there. One of the things you might expect is that different colored materials probably absorb out different parts of the spectrum, and that's why you see different colors for them. And that's what we're going to explore a little bit in this experiment. A little background on absorbance of light. Incident light, which I've represented here as basically as a light bulb, is represented by I0, 0 meaning the initial light coming in, the incident light coming in. When it goes through a sample like this, particularly a colored sample like this, some of the wavelengths of light will be absorbed out some to different extents. And so you'll measure the intensity of light on this side, it'll probably be reduced once you've gone through a sample. And this is just an indication of some kind of meter or something to read on the other side. So the idea of absorbance is you're looking at, as ugly as the logarithm thing looks, all it is the higher your absorbance goes, the more light is absorbed out from that was starting up. And the other thing to pay attention to in this experiment is that useful absorbances only go up to a value of about 2.0 at a maximum. So when we tell you to make sure that your absorbance is sort of here, make sure it is, because it means it's liable to get bigger and you don't want to shoot over the 2.0. You can get measurements up there, but they don't mean anything. And so you'd rather have measurements that mean something. If we take a look now at the path length part, we have little plastic strips. They've been professionally cut from clipboards from Office Depot. And we have red and yellow and green and blue, depending on how you define your colors. And so what we're going to do is pile different numbers of those in. So you might look at this example here as having has a red strip stuck in here. Okay, and so we have one plastic strip in there. What happens if I start piling more in? The question marks here to tell you, not tell you the answer, to have you figure it out. As I put more strips in, here's what happens is it's going to look like this, and it's going to look like that, and it's going to look like that. So I'm getting a longer path length, and I get to watch what happens to my absorbance over on the other side. If we switch that around and think we want to look at concentration, we're going to look at the mathematical relationship between the path length it goes through and also the absorbance that we see. If we go and look at solution concentrations for a minute, what you'll see here is the question is kind of, does the absorbance go up or down as the concentration goes up or down? The question again is there a simple mathematical relationship between it? So as we change the concentrations, these will be food coloring solutions. Let's go ahead and play this since I spent all the time putting it together. As you run through here, you see this is getting less and less concentrated. It's not quite as dark, and so is it absorbing more or less light? You can probably guess that pretty easily, but is there a relationship for us to look at and make some sense out of that? So this guy right here, he's sort of an electronic data logger. He's pretty much like your cell phone, except you don't have any luck making calls from him. He's bigger, he's uglier, most likely your cell phone is. On this side is a SpectroVis Plus. That's our spectrometer. You see a little color band across here. That's going to tell us what the absorbance is as a function of wavelength. And then this is just a cable that hooks them together. These are the professionally cut plastic strips along here, and this is what we call a cuvette. When we get to working with solutions, we don't want to pour the solutions into this hole in the spectrometer. We want to have a cuvette, have a holder for them. So we'll be using that when we do the food coloring and when we do the nanoparticles. So let's take a look at how this works. Let's take a look at starting up the LabQuest, seeing kind of what happens there. I'm going to actually run you through what the face looks like on the LabQuest, the steps that would be involved in that. Maybe a little tedious, but you can look at it when you need to. Hit the wrong button. Over here, right there, USB goes into here. And on the spectrometer itself, it has just a D connector. D connector looks like the letter D. And there's only one way it can go in. There's only one place it can go in. You cannot mess up the SpectroVis Plus at all in plugging it in. So let's take a look at this, at the LabQuest itself. Once I have this plugged in and get it all set to go, let's take a look at it. So let's take a look at the LabQuest, see what might happen, and see what happens. The on button, as you saw on the previous slide, is on the long end of the LabQuest to the left of where you're going to plug in your SpectroVis Plus. I can't tell you which side necessarily because they auto-rotate, so up and down, left and right always kind of change, kind of like your cell phone does. But it'll be on the long side. It'll be right next to that port where you plug in the USB port between SpectroVis and LabQuest. What we want to do is turn that thing on. You wait a little bit, and it comes on. What you might get when it comes up is a screen that looks something like what you see right now on here. It says auto recovery or remote LabQuest file has been detected. Would you like to open this file? You basically really don't, you virtually never want to open that file. If you're just starting up, you just turn the thing on, you don't care about somebody's previous file before that, just go ahead and cancel this thing out and you should be okay. So I'm going to go ahead and hit the cancel button down here in the lower right hand corner. I'm going to cancel out through that. And what you see coming up now, since I have the spectrometer plugged in, you see where it says absorbance, and you see where it says absorbance. And what you'll find out is it has got this big red bar. Absorbance reading is, you have the full spectrum up here in the upper right hand corner. You have this sort of like a normal looking menu. When you look at the LabQuest menu, you'll notice a couple things. One is up here is a little meter screen that's showing us that's the screen we're looking at right now. Over here in the next to that is the graphing mode. We'll see that one used in this particular experiment. Here's the one that lets you see a table of data. Over here you can make, you can see different experiments that are stored inside of the LabQuest, and over on this side you'll actually see the writing, taking notes and that sort of thing. What I want to show you just in this short section is setting up the spectrometer. One of the things we want to do with the spectrometer is to calibrate it. And to calibrate, if I just come into this red box here and click on that, you'll see where it says calibrate. So that's not too tough. If you click on that, it says calibrate. It comes up into this screen, and now what it's going to do is it's going to take 90 seconds. It's going to seem like 90 minutes. It's going to take 90 seconds to actually warm the lamp up inside the spectrometer. The spectrometer has a small visible near-infrared lamp in it. It has a detector on the other side, just like you saw in the crude diagram to start with. And so we're going to let this thing warm up. Actually, I've already warmed this one up, so I'm going to skip this one. On yours, let it warm up completely the first time. So we'll just skip this one up here. It says finish calibration. Just leave it empty. Don't put anything inside the chamber of the SpectroVis Plus. Just tell it, okay, I'm going to finish my calibration. And it should come back and say okay pretty quickly. And we should be all set. So I'll tell it okay, like that. Now we're all set. We're calibrated. We're set to go. We'll go through a couple slides showing you how you're going to put your samples in and make sure we have that down, and then we'll come back to this and look at how we're going to handle the data in it. So let me go ahead and stop this. I have a good day at this. If I look at up in here, I have a couple pink strips in there, and they're just lined up this way. Notice the light is over here. There's a little symbol on the SpectroVis Plus says here's the light comes out here, comes straight across there, so you want the flat face of your sample to experience that light. So you want to have it like this. You do not want to have it look like that. You're just going through the edges, then you're not changing the path length whatsoever. When we move to solutions, the key thing to remember in solutions is you do not pour the liquid into that hole. It'll come out the bottom end and probably mess up electronics on the way. What you do want to do is put it into a plastic cuvette, which we have. The plastic cuvette has ridges on two sides of it, two opposite faces. It has ridges along here and it has ridges along here. You want those ridges to be facing you when you're looking at the SpectroVis Plus this way, because the light comes from here to here, and you do not want the light going through the ridges. That will mess up everything. The light reflects, goes different ways, does all sorts of weird things, and your data will be no good at all. So make sure you put the cuvette in correctly every time. Now, let's take a look at getting some data from the plastic strip. So let's go ahead and take a look at this video. Here the instructions are exquisitely written out, but they're kind of tedious to read through a little bit, so maybe seeing one would help out. And so we've got the spectrometer up, it's running, it's already been calibrated, everything's set to go. I'm still in the absorbance mode, as you can see by what we have written up in here. Actually up here in the full spectrum absorbance mode, that's just where we came up to by default. What we want to do is we want to take a spectrum of one of these strips. So we'll just go ahead and grab one of the pink strips, pink, red, whatever it is, put it inside of my spectrometer. It's just one of them. I'm going to hit start button, and pretty much immediately what we'll see is a spectrum like that. I'm going to hit stop it. So down the red in the lower left hand corner, the red square means to stop. Looks like that. So that's my spectrum. You notice in this case, in this particular spectrum, that this is absorbance over here on the left. So the more this is, the higher this value is here, the more light's being taken out of that particular wavelength. The lower it is, the more light is passing through that wavelength. So in this particular strip, it's seeing a whole bunch of reddish, pinkish pass through, and the greens and blues and all that are getting absorbed out on that end. You might notice that up here it tells me what the absorbance value is. 1.252 is up here. It tells me the wavelength down in the lower right hand corner. So that's a pretty simple thing to do. Now what we want to do with that is we want to pick out a place on this spectrum where the absorbance is going to be on the order of 3/10 to 4/10, somewhere in there. So I'm going to click somewhere around, this is split up as 0.5, 1.0, and so on. So somewhere down in here I want to click, so I'm going to click in here, and it's about 0.383. I might go just a little bit lower than that just for fun. I'll go down to there, 0.330, and that's good. You can also click over on this side and same result. Doesn't matter. We don't care which side you go on. So what's going to happen now is we want to record the absorbance of 1, 2, 3, 4, and 5 strips looking at this particular wavelength, which in this case is 588.9. So that's good. What you might want to do with this too is for each person in your group, they need to have one printout of one of the colors of this spectrum, because they'll answer a question later on about it. So you don't need to print these out every time. You don't need, but if you all want to print 3 of these right now, that's fine. If you want to print, when somebody wants pink and somebody has yellow as their favorite color, and somebody, however you want to do it, but you need one copy of one of these in your group. And so we've got that thing in, and we're all set to go now starting to record data. So here's how it works. I'm going to come up here in the meter icon up in the upper left. So I'm going to click on him, and we're going to change the mode. And so I look up here, it says mode. If I just click on that, where it says full spectrum, it's got a drop down. So I'm going to drop it down. I want to do something called the events with entry. Events with entry allows me to let it record data all it wants, to monitor data, but when I hit and tell it to keep a point, it will keep the point, and then I can tell it something about that point, and that's what we want. So I'm going to click on there, and it's nice to average it over 10 seconds as well, just to get kind of a better run of data. These are pretty stable, so it shouldn't be too much of a problem. And it's going to say this: you've changed the mode and have unsaved data. If you wish to save or discard, we'll go ahead and discard those data. It's talking about that spectrum you just took. If you've got a copy of the one, everybody has their copy, just go ahead and discard it. You don't have to save this stuff down the road. As you can tell, running it's pretty quick. It comes up in this mode now. It's called events with entry, and here's what you see. 588.9 nanometers is the wavelength that we picked before. Make a mental note of that from the previous slide. Make sure you know approximately what wavelength it's supposed to be, because once in a while it'll come up and say 800 or something, and you're going to be all messed up. And so if it doesn't have a wavelength you think it should have in there, just click somewhere on the red strip and go down to change wavelength, and you can type in whatever wavelength it should be. So that's kind of a good check before you start doing this, to make sure you have them in place. Now what we want to do is we're going to take spectra of 1, 2, 3, 4, and 5 strips. So I'm going to go in here and head here and hit the green arrow, the start button in the lower left. And what you'll see is there's a red stop button, there's a keep button. You do not want to hit the stop button. You do not want to hit the stop button until you've collected all 5 of your strips, the data for all 5 of your strips. So click the keep button in here, and it's going to count this thing down. I have to develop a better set of 10-second jokes because I don't really have any. It comes down to here, looks like this. Boom, and we're going to tell it we have 1 strip. So I come in here and I click 1, tell it OK, and there we go. Now what I'm going to do is go in and put a second strip in. Okay, it'll be parallel to the other one. It'll be laid in the same way. And I'm going to tell it to go ahead and don't hit the red button, don't hit the stop button, hit the keep button. It's going to come up, it's going to average it over 10 seconds. And after this, we'll have 2 pieces of data done. This whole process for a colored strip might take you 5 to 10 minutes if you can get this system figured out. So now this was 2 strips. I want to click on a 2 and tell it OK. And now we'll go ahead and put a 3rd strip in. So when I put the 3rd strip in, it's going to look like this. And in that 3rd strip, we're going to go ahead and keep this guy. So you average over 10 seconds again. And then we're going to tell it that that was 3. And by the way, your touch screen, these LabQuest have touch screens. They have a stylus with them, so you can use that to get your data in, and it's fine. So there's 3. Kind of see a pattern developing there, do you? Let's go ahead and put 4 in. And we'll go ahead and tell it to keep this one and let it go for 10 seconds again. And we'll put in a 4. Tell it OK. And then we'll go ahead and put in a 5th one. And we're going to go ahead and tell it to keep the 5th one as well. He'll average them over 10 seconds. And I want to tell that that's going to be 5 strips inside of there. So I tell it OK. Looks pretty good. Alright, so there's my stuff. You kind of get a sense of it. It looks like a straight line almost, doesn't it? And one of the things you might want to do while you're at this is up here in this table, this X and Y table, you'll find in your lab book a place where you're supposed to record these. It looks like your lab book only has 4 lines on it for recording them, 4 strips. You can squeeze 5 in if you want. 4 probably is enough as well because they're pretty good. But I take and click on the XY button like this, and what you'll see is there are your data. So you can actually take your data right from here and just record those in your lab book. That's handy to have, so you don't have to go back and redo it again if a question comes up that you have to deal with. And so you can just go in there and type in, just write in what these numbers are into the appropriate places on your lab book. Now what we want to do is we want to handle the data statistically a little bit. In one of the earlier experiments, you became acquainted with hand drawing a least square, a line, making a plot, hand-drawn plot. We're going to use the technology a little bit here. Before I move to Excel in another couple of weeks, we're going to use the technology here to get the best straight line equation from these data that we can. And the way we do that is we go into where it says Analyze. Oh, wait a minute, I'm sorry. We have to stop the run. The red button at the bottom, you need to stop the run. Looks like that. I want to analyze it. So I'm going to go to Curve Fit down here. Click on that. And my curve fit data is that absorbance value I got right there. It looks like this, and we think it looks like a straight line. I think it looks like a straight line, so I'm going to click on linear. What comes up is this screen. That screen has it in the slope. You might remember the old line y equals mx plus b. M was the slope, b was the intercept. That's what these numbers are in here. Ideally, these guys would come out with an intercept of 0 because if you don't have any strips, there shouldn't be any absorbance, but go ahead with whatever value you have inside of here. And it's pretty small. B is pretty small. You could leave it out and probably be okay. The correlation coefficient is one that if it's closer it is to 1, the more linear this is. You can see this is really pretty close to 1, so this is actually a pretty good line. what you'll want to do is record that slope and intercept in your data table in the appropriate place. Okay, and so there's a place right down below the plastic strip colors, talks about the slope, the intercept, and the correlation. Record those things in there as you go, and so you can kind of figure out what you got going. Click OK on it, and that's an entire set of data for you for plastic strips. What do you do next? Grab a different color and go through the same process with it, and you'll be and pay attention as you go through it. You might ask yourself questions like, well, I wonder if the slopes are going to be the same, whether I'm green, yellow, blue, whatever I'm going to be. I wonder if the slopes depend on wavelength. You can look at things like that if you want to. So this is pretty much the LabQuest part of this. So what I'm going to do now is take us over and look at what it is we're going to do with those data once we have them. So as I mentioned, you probably are familiar with the straight line formulation. Y equals mx plus b is pretty standard. You've probably known it since you're about knee high. And so as you look at it, you recognize y is whatever your vertical axis is, x is whatever your horizontal axis is, m is your slope, and b is your intercept. Well, in our particular case here, our y-axis was absorbance, so we put him in for y. Our x-axis was number of strips, and our equation looks just the same. It's just y is absorbance and x is number of strips. Using the values we have, we got 0.299 for that particular slope, we got 0.0447 for that particular intercept. Using your skill set in manipulating straight lines, you should be able to recognize that, hey, if I know m and I know b, if I know one of these others, if I know how many strips I have, I should be able to predict what the absorbance would be by just putting it into this equation. If somebody says to me, hey, how many strips would it take to get this absorbance? I go over here to absorbance and say, okay, I want to get a certain absorbance here. I'm going to take and subtract my b from it and then divide by my m, and that's how many strips it would take. We didn't measure the thickness of these strips. We could do that, and that actually would give us a value in terms of millimeters or centimeters or whatever we wanted to do. So using that is pretty straightforward. Now, in the next part of this part one, we're going to take a look at the effective absorbance on, the effective concentration on absorbance. And when we do that is we have some stock solutions made of food coloring. And the first one we're going to call concentration of 1. It's not really one anything, it's just our most concentrated one we're going to work with. The idea is we'll make half dilutions of that, which is pretty straightforward to do. If I take one of those cuvettes and I count how many drops I can put in there, take like an even number, like 40 or whatever it is, just put them in there until it's about 2/3 full. Count those drops, that's how many drops you can put in. Then what I can do is I can take and measure my stock solution, the one that's available in the lab, and then to make a half concentration of that, I'll just take a cuvette, put in, if I have 40 drops in a cuvette, I'll put 20 in of the food coloring solution. I'll put 20 drops of water in, mix them up a little bit, get a measurement of that. And then if I want to get the next one, I'll take 20 drops of that solution, that diluted one already, and dilute it with 20 drops, and every time I cut the concentration in half. Getting the data for this is very much the same as what we did with the plastic strips, the exception being that you aren't just pouring this into the little hole. Remember, you have a cuvette, you have to put it in. Yeah, the other thing is when you hit the keep button in this set of data, what you want to make sure of is that you put in the concentrations, not the numbers 1, 2, 3, 4, 5. Put in the concentrations. First one is 1, the next one is 0.5, the next one is 0.25. They get cut in half every time. We do the same linear regression, same linear analysis, and figure out slopes and intercepts and that sort of thing as well. And the last part, nanoparticle solution. These are interesting solutions because in this image here I took from the internet somewhere, what you find out is these are all the same solution, same compounds in here. The difference is they have different sizes. The particles are different sizes. And it's not till we get down to this very small, this nano size, 10 to the minus 9th or so, we start seeing differences in colors based on the sizes of what those particles look like. So we'll explore that a little bit with 3 known solutions and make up another one and play with that and see if we can measure something about the absorbance based on that particle size. So I hope this sort of thing helps you. Get ready for the lab. It could be helpful for you to come in and be efficient and effective and actually spend a little time asking yourself some other questions as the lab goes along. If you have comments about these videos or the lab book in particular, you can direct those to your instructor, direct them to me, Gary Buckley, just gbuckley@cameron.edu, or you can call me, or you might see me in the hallway, that sort of thing, and that's fine because we're just trying to make sure we're trying to get better all the time as we do these things. So thank you for your time.